Good afternoon. Hope you're enjoying your lunch. So we're going to talk about machine learning today and how it impacts some of the IPs that we're working on at my company. So I wanted to kind of take it up a level and look at the design targets that we're reaching for. So this is the human brain. This is your design target. We're looking at something that consumes 20 watts in power consumption, has an amazing amount of storage, 2.5 petabytes. In fact, I didn't know what a petabyte was. I had to look it up on Google. A petabyte is 1,000,000 gigabytes. I still couldn't conceptualize 1,000,000 gigabytes. So essentially, it's the storage capacity of 300 years of video constantly running. The human brain is 30 times faster than the fastest computer of today. So that's your design targets. Pretty simple, right? Artificial intelligence mimics human behavior. I'm going to talk about some of the research and work that's going on in artificial intelligence chips. And I've got a very nice reference that I got from a contact of mine, Dr. Barbara DeSalvo, who works in Grenoble. And she presented it as part of her keynote at the ISSCC conference this February. What she did is she compared computing efficiency in giga operations per second per watt against computing performance. In that comparison, she took an insect, this example is a honeybee, and mapped on the human brain. Okay? And as an aside, I was preparing this presentation. My 5-year-old son was very curious about what I was so busy with over the last few weeks. So I explained to him that I'm trying to give a presentation on how people are trying to develop artificial intelligence and computerized brains. And I gave him this example of a honeybee. So this is my 5-year-old son. He's at pre-kindergarten. And he'd been studying honeybees with his kindergarten teacher. And he told me something very interesting. He said that the honeybee, or the worker bee, when it goes into its nest, it dances in a figure of 8 to communicate to the other workers the food source. Pretty impressive piece of information, and how that links from a honeybee's brain to the brain of a 5-year-old. So let's get back into the comparison Dr. DeSalvo made of the state-of-the-art artificial intelligence chips. Some of you are probably working in these companies, and I think it's very interesting to make the comparison. So the first thing that comes across in this is the relative scale of all of these artificial chips in relation to the human brain. In terms of power consumption and pure processing speed, they're not quite there. So I'm going to touch upon a few of the interesting chips that have been released this year, or the last couple of years. So I'm going to look at the Google TPU, the Tensor Processing Unit. Okay? This has been designed for the TensorFlow framework. It's a symbolic math library which is used for machine learning applications, such as neural networks. The other example on the edge of this diagram is GraphCore. GraphCore is a company in the UK. A lot of the engineers came out of InMOS and some of that parallel processing legacy. And their chip is called Colossus IPU. It's a great name. Colossus Intelligent Processing Unit. It has 1,000 processors. They perform deep neural networking performance, and their claim is that it goes beyond GPUs. They use huge parallelism in their design in order to achieve DNN, deep neural networks. It can take weeks to months to train a new neural network. These chips that are being released this year are probably the largest, most expensive chunks of commercial silicon to date. And just to close out, inspecting the latest set of designs and making the comparisons between Intel and NVIDIA, I'm going to show an example of NVIDIA's Xavier chip. This is 9 billion transistors. It's an 8-core CPU. It uses 512 Volta GPUs. It has a new deep learning accelerator, which can give you 30 trillion operations per second. It consumes 30 watts. Still, it's not close to the target of the brain, which gives me a lot of comfort, actually. In order to tackle the problem, there's a classification that's happening in artificial intelligence. The first chips that came out, an example was IBM's chess game. This was Deep Blue. Artificial intelligence mimics human behavior. Machine learning uses data and algorithms to progressively improve performance on a specific task, such as facial recognition. Deep learning mimics the neural networks in our brain. So, in order to mimic human behavior, in order to do artificial intelligence, to develop a chip, there's a couple of classifications that are happening. You have training, and you have inference. Okay? The training typically happens in the cloud. These are big chips doing huge data set analysis. The inference happens on the edge device, and this is where you have things like facial recognition. In terms of the training stage, again, up in the cloud, you use large data sets. This is like a collection of images. You use machine learning frameworks developed by companies like Amazon and Google, namely Caffe2 and TensorFlow, in order to build mathematical models. This is done in the cloud, or it can be done on your desktop. The inference stage, this is your edge device, your mobile phone that does facial recognition. This optimizes a model with tools. It uses real-time data, and it's done on end devices. So now I'm going to take this concept and start getting into the world of chips and semiconductors. Artificial intelligence leading to machine learning chip architectures. So on the left, you see the training in the cloud. On the right, you see inference happening at the edge devices. Okay? I've made this analogy very simple. In fact, there are hybrid chips that sit between the two. Okay? The key here is the efficient movement of data. The goal is to reduce the need for artificial intelligence updates from the cloud. The training cloud applications include healthcare, financial modeling, weather prediction. On the edge, you have facial recognition, natural language processing, object identification, and a new concept called 5G self-optimization. Always, the key is to develop efficiency around the inference. And this is done through a concept called pruning and quantization of the models. Okay?
Audio is okay, or I need to? Okay.
Now we get into more of the design challenges. And these point to the amount of memory bandwidth, and capacity. We look at low latency for the cloud connectivity. And in order to make the processing efficient, especially on the edge, you can look at things like domain-specific processors. So we'll cover all of these topics during the course of our presentation today. So let's look at the memory bandwidth and capacity. Generally, these chips communicate to an off-chip memory, right, to a DRAM. What's happening is that these DRAMs are not keeping pace with the scaling that was defined by Moore's law. So you can see that if you compare the orange line to the green line. The CPU performance, the SoCs, have done a great job in scaling with Moore's law, but the DRAMs are somehow struggling in order to support that scaling law. The memory bandwidths for some of these applications are outpacing the capabilities of DDR. These applications include high-performance computing, network applications. The DDR performance, the DDR is the technology that connects to the DRAM, is limited in its nature because it's a parallel interface and it's a non-embedded clock. DDR4 is moving to DDR5 for servers. In terms of the edge devices, the implementation is low-power DDR, and that's moving to LPDDR5. And there's also a concept in this parallel world of graphics DDR. GDDR5 is moving to GDDR6. Okay? So the key points to absorb as we're going through this presentation are really the bandwidth, the capacity, and the power. And we'll do that in relation to the performance and the latency as it interfaces to a high-speed memory. What I'm doing here is I'm comparing the state-of-the-art high-speed memory interfaces in terms of their capacity and their bandwidth. Okay? So we have DDR5, GDDR5, GDDR6, LPDDR5, and then a new classification called HBM, high bandwidth memory. DDR5 is essentially a dual 40-bit interface, so 32 bits of information, 8 bits of error codes, and that gives you a total of about 80 bits. Each channel can support up to 3 DIMMs, dual inline memory modules. On the other hand, high bandwidth memory works very well in parallel computing applications. It's used for specialized accelerators for deep learning. You can connect the HBM to a host SoC by a 2.5D interposer. Okay? We'll get into some of these details later. HBM is a very wide bus operating at modest data rates. 1,024 data bins are available per HBM stack. You can stack these up to 8, which increases your capacity. It's a point-to-point interface with double data rate signaling. You add capacity by stacking the DRAM die using through silicon via technology. Okay? So what machine learning is doing, it's changing the way the packaging is done for a lot of these high-speed interfaces. And it's opening up opportunities for through silicon via 2.5D packaging. Remember I said capacity and bandwidth are very important when you're developing these devices that go into the high-speed data centers? Let's look at this in more detail now, comparing DDR5 and HBM2. So I've color-coded it here, green for capacity, blue for capacity, green for bandwidth or speed. So this slide shows 5 versions of DDR. The one at the top here, this is DDR5. It's implemented in a 3D package. Okay? So you stacked DDR5 SDRAMs using through silicon via. What this does, it increases the capacity. There are other implementations of DDR, which you can see here in terms of form factor. You can use LR DIMMs, you can use resistive DIMMs, you can use UDIMMs. Okay? If you're comparing it in terms of bandwidth, clearly the green is a winner. HBM is the winner. So this is a very interesting trade-off in terms of capacity versus bandwidth. So if you want capacity, if you want bandwidth, you have to decide between DDR5 and HBM2. And in many cases, and I'll show you some examples, a lot of these chips implement both. So the HBM DRAMs include 2, 4, 8 DRAM die stacked inside a package. In the previous slide, I showed graphics DDR, GDDR5X, GDDR6, and you may be wondering why I'm not highlighting it here. Well, one of the challenges with graphics DDR, and the topic of the talk, is getting your power consumption down. Graphics DDR is very high in power consumption. So it gives you some of the benefits of capacity, but you lose out in terms of power consumption. So let's compare this in terms of the goal, which is near zero energy. Okay? So this is a very interesting comparison of the SoC DRAM PHY energy efficiency between DDR generations and HBM. So just to give you a bit of background, the energy efficiency of the SDRAM is the energy consumed to read or write one bit of data from or to the DRAM. This is typically expressed in picojoules per bit or milliwatts per gigabit per second. So for the host SoC, you can use the same metric as the power efficiency of the PHY. So this is a very smart way of looking at the power efficiency of the DRAM and of the DDR or HBM IP. Clearly, the winner here in this comparison is HBM. Okay? So great. We have a solution to get the energy consumption to an interesting capability and also have some reasonable speed, bandwidth, and capacity. But that's not the end of the story. And this is kind of interesting. So I'm going back, I'm comparing the DDR5 system with the HBM system in a system, right? DDR memories are connected in a DIMM format through a memory controller. There's a bank, there are bank rows, there's a bank activation that manages the memories in the DIMM. So these acronyms that you see here, the timing for the 4 activation window, the TCCD, the TRRD, are related to the bank row activation commands, and they're used to tune the energy budget within each rank. The TCCD is related to the prefetch cycle, also in the bank group. Bottom line, more channels is always better. The engineers at the system level can do some optimization in terms of the system and thermal performance by playing with these parameters. At the board level, the DDR DIMMs are often orthogonal to the motherboard, which allows fans to dissipate the heat. If you compare that with HBM, you have much less volume per gigabit per second. The DRAMs, the HBM DRAMs, are in the same plane as the host SoC and the motherboard. This means that the DRAM is closer to the host SoC. This allows you to do things like liquid cooling. So the example I'm giving for HBM is from AMD. It's the Radeon Fury chip, or graphics card. So although you can get the power consumption down of your SoC, meeting the near zero energy target, your system may still require a lot of cooling. So recent examples. This real product, Intel with their Stratix Altera implementation and AMD's Vega 10 GPU. Both are using HBM and DDR. That's the key point. Okay? The HBM2 stacks give you 4 gigabytes each with 10 24-bit wide interfaces with a total of 2048 memory interface to the SoC. Intel uses an interesting technology called embedded multi-die interconnect from the external world, which is your PCI Express, into the HyperFlex architecture. So I gave you some perspective of capacity, of bandwidth, how that relates to power. So I want to summarize this section. So machine learning chips use both DDR for capacity and HBM for bandwidth. HBM2 has the lowest picojoules per bit. I'm going to move to interface IP. So you can think of your brain as the processor, your eyes and ears as the interfaces, okay? And how deep learning can impact the specifications of your interface IP, like PCI Express. I introduced this topic with a deep neural network application, vision processing. So let's stay with that theme. This is a really, really interesting statistic. This shows the rate of improvement of deep learning approaching human levels for image recognition. If you look at the dotted purple line that's going horizontally at the lower part of the slide here, these models are actually better than humans. These models have less error than our eyes. That's great. How do you implement these models on your chip? Remember, we had these issues about capacity and bandwidth, right? And power consumption. So I'm going to look at two of these models and walk through some of the challenges in terms of optimization of the model in order to service the amount of available memory that you have in your SoC. So these two deep learning models are called ResNet and VGG. The way they're defined is through layers. So the bigger the number, the more deep you go into the learning profile. So 50 layers for ResNet is deeper than 19 layers for VGG. The top of the ResNet deep learning platform goes to about 200 layers. So that's very, very deep learning. So I'm going to take those two. And what I'm doing here is three things. We have the memory size and the model. And I'm doing the three things, which is looking at the training model required, or the training memory required, the original inference model, and the optimized inference model. Remember, I provided these concepts of inference at the edge devices and training at the cloud. Okay? So this is where you see it in action in terms of deep neural network training. So deep neural network training causes three issues for interface IP. Capacity, like we had the same issue with memories. Irregular memory access, and bandwidth. The capacity can be solved through virtualization techniques. Okay? So I'm not going to talk about virtualization. We've done had a lot of discussions about virtualization in the past. But essentially, machines can be virtualized, and that handles some of the capacity challenges when you're implementing a very deep neural network and you're starting to optimize the amount of learning through inferences. The other two challenges we're going to cover now, and I'll give you some interesting examples of a real application and how we can solve it by looking at deep neural network engines and some new interfaces. Okay? So key thing here is that the optimized models increase the irregular DRAM access, potentially causing cache misses in your memory, which makes cache coherency very important. So I'm going to introduce the concept of cache coherency. Okay? So this is an example of irregular memory access. What you're seeing here are two processors communicating with the caches to the memory. The cache needs to own the data in order to make the update, and it needs to communicate that ownership to the other memory locations. So in this example, P1, your processor, the cache is not communicating the ownership to the other locations before making an update. Therefore, what happens is that the different caches end up with different values and ultimately corrupting the data. So 8, 10, and 10 are incorrect in terms of the memory locations when you originally started with the processor data. So this is irregular memory access. It happens because of the pruning and optimization that's done to the deep neural network algorithms. All right. There are three possible solutions to this problem. Number one, you can remove the cache altogether. Okay? That's kind of like a major surgery, you know. You can kind of survive, but the performance isn't quite acceptable. Option two is a software approach, which has been done for many, many years. It's to use semaphores, and the semaphores are coded. They have lockout regions. It's kind of painful in terms of software development, and it is lower performance because of the checking semaphores you have to use. Option three is to solve the problem using hardware. So multiple CPUs, P1, P2, are working on the same set of data. Before P1 writes the data, it gets ownership of the data before modifying it. With the caches communicating with the others before modifying the data, we avoid data corruption. Okay? So I have to thank my team, Richard Solomon and Scott Knowlton, for helping me through these slides. And Richard would actually be talking a little bit more detail about PCI Express Gen 5 and other very interesting topics later on this afternoon. So in order to address the bandwidth challenge, so I talked about irregular memory access. In order to address the bandwidth challenge, let's take a step back and look at the overall architecture. This, hopefully, you'll find interesting. So this was from a paper I got that was published, and you can see the location of the publication. Very interesting paper. And it took an NVIDIA chip, the Titan X, connecting to basically a PC-based architecture using an Intel chip. So this is something that was done, a year or two ago, so fairly current. And it's connecting these two chips for deep neural network applications through a PCI Express interface. Okay? And you can see the memory access with DDR and GDDR. Now, we've had a bandwidth problem. We want to solve that bandwidth problem. So this is a proposal, and this is essentially what's happening, right? If you kind of open up the packages of the chips that are described at the beginning of the presentation, these are how people, engineers, are starting to architect these training architectures. They have a deep neural network engine talking to an apps processor, which is also a deep neural network engine. They're communicating with something called C6, which does your cache coherency. So option number 3 on the previous slide is now implemented in the training architecture on this slide, okay, here. The bandwidth problem is solved simply by increasing the speed of the interface IP. So we went from 8, which is PCI Express Gen 3, to something around 25 gigabits per second, which is the C6 specification. C6 also supports PCI Express Gen 4. So you get the ability to support both C6, cache coherency, and PCI Express Gen 4. In terms of the bandwidth issues on the memory side of things, this implementation uses HBM2, giving you a phenomenal capacity and bandwidth, okay, which you can see the numbers here. And also it implements DDR5. This isn't the end of the story because people are innovating today. So I've actually seen specifications to increase the speed of HBM2 to something called HBM2E. So you're going from 2,400 megabits per second to around 2,800 megabits per second. So this bandwidth issue is being dealt with a higher memory interface. So those two problems are highlighted in terms of irregular memory access and bandwidth are solved. Firstly, you can use faster interface IP. PCI Express moving to PCI Express Gen 5. You can use C6 going up to 25 gigabits per second. Irregular memory access is handled through cache coherency. What's actually really beautiful, I think, about this system is that all of this is now one cache coherent system. Okay? It's no longer a concept of two chips. It's one cache coherent system. So you could put your CPU, GPU, your CPU in this format, and they wouldn't be corrupting the data and operating at very high speeds. So now I'm going to take this concept and show you what can be done with a fabric. And I'm going to use some technology developed by our partner, ARM, in this example. So that purple block I showed at the beginning, which was C6, sorry, in the previous slide, which was C6, is now blown up, right? So this is what it looks like inside. All right. This connects to an ARM fabric using these two commands, the CXX and the AXI. Okay? So what we're looking at is a fabric used to connect the CPUs, the accelerators, and interfaces to the shared memory resources. Right? These can be hundreds of units. The orange path on the left, so this is the C6 part, shows the commands, the cache coherency commands, passing to the fabric which executes these commands. So again, this is an example where C6 IP is interfacing with ARM's Core-Link 600, CMN 600 fabric. So this is what gives you a cache coherent fabric. Okay? Back to power or energy. This is probably one of the most exciting areas in terms of innovating new architectures, both in terms of RTL or digital design, but also in the physical design in terms of mixed signal innovation. So here we're showing some advanced energy management using PCI Express Gen 5. Remember, faster interconnect solves your bandwidth problem for deep neural networks. So fundamentally, PCI Express Gen 5, with a lot of these standards, there's a specification. But following the specification in terms of optimizing for power consumption isn't enough. You have to look at both the active and standby power. So what I've done here is I've underlined some techniques that we've used to accomplish much lower power than just following the power consumption, just following the specification. So from a digital perspective, L1 substates, something called SRIS, which is separate reference clock with independent spread. Okay? DPA, which is your dynamic power allocation, and OBFF, which is essentially your optimized buffer fill, allows you to be able to control both active and dynamic power consumption. The dynamic power consumption in the physical interface, remember, 70% of the power consumption in this interface actually comes from the output transmitter of the high-speed PCI Express Gen 5. So if you can get the power consumption down of that 70%, you're getting towards your goal of near zero energy budget. So some of the techniques that we're using include optimizing the driver by playing with the launch amplitude, looking at the noise profile, and essentially looking at the design from a common mode architecture, a current mode architecture and a voltage mode architecture. And you're making those trade-offs in terms of power supply rejection ratio and launch amplitude. PCI Express Gen 5 has a very interesting specification related to the channel, i.e. you're communicating between two links across PCI Express Gen 5. The bit in between, the medium in between is called a channel. It can be a board FR4 material that can generate noise at very high frequency. So the equalizer used on one end helps to recover the noise, helps to recover the signal in the noise. And if you reduce the power of the DFE, if your channel is benign, you also save on power consumption. You can also do tricks like reducing the transmitter supply voltage and underdrive it, and that helps save power consumption. You can use other techniques, and we've tried these, like power gating, power switches. And this also helps in your L2, L1 modes. Again, these are defined by the specification. And this really helps in getting the power consumption down. And what we've seen in terms of standby is that you can reduce the power by up to 95% on the controller, on the digital piece, and to about 100 microwatts on the PHY. And that's getting close to the leakage current in a 7-nanometer process. So this is trying to give you at a very macro scale. If you activate one of these switches, you can basically shut off a large part of your design and just keep kind of a lifeline going for your PCI Express system, which are the critical elements. Right? So I covered a lot in this section. Just to sort of recap, the key points I made is that capacity can be solved by virtualization. Irregular memory access can be solved by cache coherency. Bandwidth can be solved by faster interfaces. To get your power down can be done by using advanced energy management techniques. All right, let's go to the cloud. So remember at the beginning, I divided the problem into two. You got your edge device, and then you got training that happens in the cloud. So let's talk about the chips that are used in terms of cloud connectivity. This is a very interesting chart. It shows the speed in terms of different lanes with the speed of the individual blocks that make up the high-speed interconnectivity, okay? So what this does, it helps you decode the lane speed in terms of the overall speed of the system. So in terms of a timeline, you can see that in 2015, the state of the art was 50 gigabits per second with a by 2. Today, the data centers want 50 gigabits per second on a single lane. Okay, so that's the key point. Okay? Again, by 2 a couple of years ago is now by 1. Okay? People are talking about 100 gigabits per second. Okay? What that means is that today, 2 lanes of 100 gigabit per second are used, and eventually that will transition to 1 lane of 100 gigabits per second. That's a big deal in terms of the high-speed SerDes architectures that are being developed. The interconnectivity that's used in the data centers is typically Ethernet. The data centers now have a concept where they're using hyperscale, and this is really interesting too. So hyperscale is the ability of an architecture to scale the computing and storage appropriately as your demand goes up. Okay? What this is doing is it's pushing the Ethernet speed roadmap. It's pushing the Ethernet speed roadmap, as you've seen here, but it's also creating new Ethernet standards like real-time control or time-sensitive networking. So the first 2 are really implemented for the server interface. The second 2 are designed for your leaf-spine interface. This is kind of a technical way of describing the situation of the market. Another way to think about this is that in the past, people used to think about data centers and enterprise as one bucket. Today, data centers and enterprise are 2 distinct markets with their own interface and speed requirements. Data centers are really pushing the speed. So a data center, Google, Amazon, Facebook, for example, they're pushing this envelope. They want connectivity and speed in this arena. The enterprise market is becoming commodity. The racks consume much less power consumption, and they're interested in optimizing the power for a 56 gigabit per second technology. This is a diagram to show the data center network infrastructure going from the core switch router all the way down to the top of rack. So most data centers are architected on a three-tier topology. The cloud data centers are migrating from the traditional the traditional three-tier to a flattened two-tier topology. As I mentioned, hyperscale data centers are becoming larger, more modular, and more homogeneous. A lot of virtual machines are used in these implementations, and there's a ton of traffic that goes east-west now. Okay? So the data centers are communicating across the network in terms of their workload. Getting to the power consumption requirements, this is an example of an Ethernet MAC that we're working on in my company. This is an enterprise Ethernet MAC. It supports up to 100 gig data rates. It has a 128-bit transaction layer optimized for packet-orientated transfers. In terms of power, it supports the disabling of the data memory RAM chip select when you're in the mode of reducing power. A couple other key points is that energy efficiency is supported, and there's a wake-up mode that supports things like magic packets and advanced VLAN filtering. In terms of the high-speed PHYs for the enterprise market, the state-of-the-art is 56 gigabits per second. PAM4 is used in order to save on power consumption. This is another technology that we're working in at my company. This describes a design that can go up to 400 gigabit per second Ethernet. It supports long reach, supports very, very lossy channels, up to 35 dBs at 14 gigahertz Nyquist. It's using a voltage mode design on the transmitter to save on power consumption. Also, this is using an analog front end with 32 time interleaved successive approximation data converters. Okay? So the key points in this section, just to recap, is that the data center and enterprise are both bifurcating into two markets. The data center is pushing bandwidth, enterprise is pushing energy consumption. The ways to reduce energy is to look at energy efficiency on your MAC layer and to implement a low-power PAM4 SerDes. Domain-specific processors is the next topic I'd like to cover. And the reason I was triggered to include this in the presentation was that I was reading a very interesting book that was released earlier this year by John Hennessy. It's a computer architecture book. It's on its 7th edition. It's a fascinating book, especially for me, because I've been educated on von Neumann architectures, and this actually does a lot of great comparisons of, say, x86 with the A53 and Google TensorFlow type architecture. So thoroughly worthwhile going through that book. What Hennessy talks about is the fact that all the traditional scaling laws, Moore's, Dennard, Amdahl, are slowing down. This means you have to do a few tasks, but do those few tasks extremely well. So it's all about focusing your processor architecture on a few simple but very high-quality tasks. One of those high-quality tasks is facial recognition. This is an example of a algorithm using CNN, convolution neural networks, in terms of domain specificity of a processor. So the key points here is that the transistors that were used to develop the processors in the past are not getting any better. The power budget is not getting any higher to allow you to do more processing. So the only path you have left is to use specific architectures and specific algorithms in order to support functions like facial recognition. So just do a few tasks, but do them very well. The way we've implemented CNN, convolution neural networks, is using an embedded vision processor. Okay? So this is an example of what we've done in my company. This is a wide vector digital signal processing system. it supports a full range of vision processing algorithms. Some interesting data points. It can support up to 64 max per cycle per vision CPU, and you can go up to 4 vision CPUs in this design. The CNN engine is scalable up to 4.5 Tmax per second performance, and it supports all the latest CNN graphs like YOLO, GoogleNet, ResNet, SqueezeNet, etc. So it's a standard-based tool set. It's domain-specific. It does vision processing very efficiently. Technology innovations. So this is something where I wasn't sure where to put it in the rest of the presentation, so I basically put it at the end. But it hopefully gives you some seeds of ideas, so as you're at home, at work, I'm generating new links in your synapses in your own neural nets. We run a lot of statistics at Synopsys. We have a lot of customers building state-of-the-art SoCs. This is a survey we ran very recently. It's about 800 engineers. The question was, what type of low-power design techniques are you using? And so these are techniques that they're planning now, next year. And I wanted to highlight the 2 areas that we were speaking about, so cloud computing and edge devices. So the edge devices is the bigger column here. And I'm not going to go through all of these. I think a lot of you are familiar with a lot of these techniques. You're engineers yourselves. But the multi-bit cells, which is more closer to the IP portfolio that I work in, is interesting. So this is actually a multi-bit cell for a logic library element. So this is a foundation block that you have in your RTL. So the multi-bit cells reduce power consumption. They can significantly reduce the number of individual loads on the clock tree. The clock trees are getting massive, by the way, in these designs. You know, people have up to 800 clocks on their SoCs. This reduces the overall power used in the clock tree. The area and leakage using these multi-bit cells can also be reduced by simply sharing the clock inverters in the flip-flops with one structure. You can also do things like power optimization kits that reduce the overall leakage. You can use power gates, level shifters, always-on cells, retention flops, and isolation cells. So very interesting innovations that are happening. As part of the technology innovations, I always get the IMEC report. IMEC is the research institute in Belgium for microelectronics, and I get their reports every year. And this is how they represented some of the scaling that's happening and innovations that have gone along the path. So this represents the actual transistor scaling that the foundries are producing. This kind of represents what should have happened if you followed Moore's law to its literal conclusion. And then you can see some of the innovations, right, that have been happening in order to support that scaling. So the advancement of FinFET technology, the implementation of EUV, et cetera, et cetera. What I like to highlight is a couple of things here. So firstly, the logic libraries, the Ts, right? So you move from 9-track libraries to 6, 4, maybe. So the low track height in a library helps you to reduce power consumption. If you increase the threshold voltage of that library and add long channel variants, you further reduce your power consumption. That's one point. The second point is this concept called DTCO, Design Technology Co-Optimization. This is a fascinating topic, and what this says is that you link your lithography, which is shown in this slide, with your EDA tools, your logic libraries, and your TCAD, and by linking them all together, you can do an optimization that can improve performance and reduce your power consumption. So this is an example of the transistor optimization that can be done using TCAD software. So this is comparing FinFET devices and the different types of fins that people are talking about getting below 5 nanometer. What do I talk about this? Well, these machine learning chips are getting to the size of the reticle. They're pushing the envelope in terms of the process nodes up to or down to 5 nanometer and beyond. People are looking at new FinFET structures in order to support that roadmap. And these are some proposals that are going on. So a little bit more detail in terms of using design technology co-optimization at 5 and below on logic library elements. The key point on this slide is that you can optimize the power consumption of your foundation elements in your SoC in order to improve performance. This is work that we did with Applied Materials and Qualcomm in order to optimize the foundation elements of a logic element. All right. So I didn't get dessert, and I don't know if any of you got dessert, but this is dessert, okay? So I started my career in Europe doing low-power design. My thesis is on micropower operational amplifiers operating in weakened version, okay? So I would always use the opportunity to find a slide that I can present at these conferences, and everybody hates it because it always has equations. But what's interesting is that this equation describes the current in weak inversion. So this is the current where the voltage is below the threshold voltage of the MOS device. So this is when the transistor is almost off. This is very similar to the way the synapses work in the brain. So this is fascinating, right? That you can start biasing MOSFETs to a point where they start to behave like the synapses in your brain. They have phenomenal characteristics. Actually, when I was doing the rehearsal, I went 20 minutes on this slide, but I promised not to do that. They have phenomenal characteristics that you can see here. So you push down the gate bias, your gain increases, you get better transconductance, you get even pretty good bandwidth. So subthreshold analog can mimic the brain's nonlinearity. Asynchronous digital designs help in power consumption. You can remove the clocks. You can use things like nanowires and nanowire memristors that also kind of mimic the way the brain behaves. All right, to summarize. So machine learning is used for training. It's used for inference applications. Hopefully you got the idea when I showed you those examples. It has a big, big impact in the IP requirements in terms of capacity, bandwidth, latency, cache coherency, and power. The energy budget can be reduced significantly, and you need to look at new architectures in order to do that. I talked about the new architectures for interface IP, and I gave an example of a domain-specific processor. I also introduced the concept of DTCO, Design Technology Co-Optimization. And this is very interesting because what it does is that it links process development, TCAD, with device physics, with lithography, with your logic libraries, with the EDA software. And we believe it's mandatory for doing development at 5 and below. Thank you. So this is just a quick wrap-up of the IPs that we talked about in terms of the interfaces. And finally, I'd like to thank all my friends that helped in producing these slides. And if you want to contact them, feel free. It's basically their first name dot their last name @ synopsys.com. So please don't contact me. Contact these folks. Thank you very much.